So next up we have two speakers, Karl Fosaaen and Thomas Elling. Karl's the VP of Research at NetSpy, not NetSpy, by the way, NetSpy. Thomas Elling is the Director of Cloud Pen Testing as a security researcher at NetSpy. They focus on web application and cloud security testing. In this talk, they're going to be discussing how the Azure Function App service is utilized by Azure customers and some of the architecture design flaws there that can lead to privileged escalation scenarios. So please give a warm welcome.
All right, thank you for waiting in line today and taking the time to be here for the talk. Just kind of quick rundown of who we are. That was a great introduction here. Just other thing to note here, 2021, I helped co-author the Pen Testing Azure for Ethical Hackers book with David Occhiotti. Thomas was our technical editor, or one of our technical editors on that, and made the book what it is, so thanks to him for that. Additionally, at NetSpy here, we are going to be talking about some microburst tools a little bit, but one of the tools that we created at NetSpy is microburst. Thomas and I have both done a lot of work in that space, and yeah, we're cloud researchers that work at NetSpy. So before we get into the actual research that we're going to present here, all of our research is kind of built off of the work of others, like any other security research that's out there. So please take pictures of this. We'll put the slides out after the talk here, but go read their research because, like I said, all of the stuff we're talking about today is really built off of the prior research from a lot of these folks. Some big ones here, storage account abuse for the kind of top 3 items here. We're going to be talking about that in Thomas's section. MSRC's got some best practice recommendations, and we got some kind of workaround stuff for that. And then the last couple here is really what you can do once you get access to an Azure Function App key and abusing that and getting access to managed identities, those kind of things. So before we get into function apps themselves, app services is the underlying Azure resource type that function apps are built on. So quick primer on app services. It is your serverless application hosting service within Azure. It's pretty simply or aptly named. It's application services, app services. It's all container-based and really easy to host web applications through. If you want to throw up a really simple website, app services is the way to go. The URL structure is pretty simple here. You've just got appname.azurewebsites.net. Handles custom domains as well. This also makes it a prime target for subdomain takeovers. If you're doing external recon, bug bounty, anything like that, and you find DNS records pointing to azurewebsites.net, just do a quick check to see if that actually resolves anything. Because if that doesn't resolve anything, you can fire up an app services application, take over that subdomain. Pretty handy. The app services resources support integrated authentication, be it Azure Active Directory, soon to be Entra ID, Apple, Facebook, Google, any of the other OAuth providers that are out there. If you missed it, a few months ago, Wiz put out the Bing Bang vulnerability, which relates to these authentication providers. Namely, Microsoft had the Microsoft authentication provider that allowed pretty much anybody to sign into their tenancy and then modify Bing search results. So like the top results that came back. Really, really cool bug. So definitely check that out. So with the management side of things for app services, you've got a management console that's built into the Azure portal. Makes it really easy to go in and execute commands in those containers. If you don't like that one, there's a secondary one called Kudu, which does the exact same thing. You can also get access or easy access to the app services files there. The service itself supports managed identities. If people are not familiar with managed identities, might be a little bit more familiar with kind of the same type of idea within AWS, which would be passing a role to a service. Managed identities, you're basically specifying a identity to tie to a resource or potentially multiple resources in the case of user-assigned managed identities. Then you apply permissions to that managed identity. So we can add a managed identity, give it access to a key vault, give it access to other Azure resources to do things within Azure or Azure Active Directory, and that helps support the service to build things that you want to build. So that's managed identities. We're going to play around with those in a little bit. This is also technically inclusive of function apps. So to give you the quick primer on function apps, this is the subset of app services used for just specifically hosting APIs. If you look at our example URLs here, we've got azurewebsites.net, You also see the API HTTP trigger 1. This is how you know that it's a function app. You're going to see the /API and then the name of the API trigger, in this case HTTP trigger 1. That's one of the default names here. That's a dead giveaway that it's a function app. Now, it's not to say somebody couldn't spin up an app services application, have a /API endpoint, and then, yeah, it kind of looks like a function app. But either way, that's what you can expect here. In this case, the function app is named NetSpy, so we get that NetSpy subdomain for Azure websites. Then our trigger that you're actually going to send API requests to, HTTP trigger 1. Really simple. You can have either Windows or Linux-based containers to run your application code. You've got a number of different programming languages that you can make use of. I primarily like the PowerShell ones because I write everything in PowerShell. But you can use .NET, Node, Java, all sorts of stuff. This also has the console and kudu interfaces, so some of the attacks that we're going to talk about today, you could technically replicate those through those. You do have to have contributor level access to the resource in order to run those commands, but you might want to make use of some of these attacks that way. So keep that in mind. Last couple of things here, it does support managed identities like we talked about with app services, and just general practice. If you want to spin up a really lightweight API, let's say you don't want to use Burp Collaborator to catch some kind of server-side request forgery coming back, you can just set up an API URL right here in Azure to capture whatever data is coming back, spit it out to your console log right here. A lot of the Azure IP space is going to be open for most things that you might be getting, say, server-side request forgery for. So it's actually really nice for handling callbacks for stuff. So something to keep in mind. Plus that code test just makes it so much easier to modify files and write things kind of on the fly directly in the portal. So for authenticating to function apps, you've got the management plane where we've got standard Azure RBAC, contributor, reader, all of those kind of things. That's how you manage the actual resource. In terms of getting code access to the resource itself, you've got the master key, which gives you full control over the app. That's all of the individual functions underneath it, has full control over that Azure resource. The default key that's tied to the function app allows you to execute any of the functions underneath the function app. You've got your function app and the individual functions underneath that. Under those individual functions, you have function level keys, and those have the ability to execute your functions all the way down there. You can also have anonymous functions as well. You just set in your function.json anonymous as your type, and then anybody can call those APIs. If you do have integrated authentication like Azure Active Directory or requirements for that, that is going to mess with the anonymous side of things, so that can potentially throw off some of the attacks that we're going to talk about today. But if you need to front that with existing authentication, you could potentially do that. And last part of this, which we'll pivot over to Thomas here, is that the service, function apps, is supported by another Azure service called storage accounts.
All right, thank you, Karl. So this is where things get a little bit weird. So when you are prompted, or when you do create a function app, you're usually prompted to create a storage account along with that function app. And basically, the whole role of that storage account is to kind of provide support for the function app. And really what we're interested in here is blob storage and Azure file shares. So queues and tables are also used to a certain degree with certain trigger types, but really we're really just going to look at container files and Azure share files. So in terms of those container files, that's really just used for saving state, web jobs data, and things like that. But the things that we're really going to be looking at here is application and function keys. And those are stored in encrypted format in host.json. So if you take a look at the screenshot over there, you'll see two containers, Azure Web Jobs hosts and Azure Web Jobs secrets. Azure Web Jobs secrets is where that host.json file lives, and that's what we're really going to be getting into here. And then the other thing that's interesting is file share files. This is going to be your application code, your source code for triggers, log files, and things like that. And this is going to be primarily used by default in your consumption and your premium plans. And there's options to change that, but that's really what we're going to be looking at. So, and again, queues and tables, but not really what we're focused on here. So that brings us to key decryption. So when we're talking about key decryption, we're talking about decrypting the access keys. So your master, system, and kind of function level keys for your function app, right? And the interesting thing here is that those access keys can be decrypted within the function app container runtime while you're running triggers and offline. This works with Windows or Linux with any runtime stack. So it doesn't matter if it's Python, PS Core, or anything like that. If you have the decryption key, you can really do whatever you want. So that brings us to the 2 requirements here that you absolutely need to have. So number 1 is access to that encrypted material, which is kind of your encrypted master key, function keys, and things like that in host.json. So you need to be able to read that. And then to actually do the decryption, you need access to an environment variable within the function container. So bottom line, you need some sort of command execution to kind of get at that environment variable in the container. We did report this to MSRC, and it was confirmed to be expected and documented behavior. So really what we're going to be talking about here is if an attacker is in this position where they have the read and write access to the corresponding storage account, what can they do and how can they affect that function app? So let's talk about permissions here. And before we kind of get into that, all of the permissions that you see here and that we're going to talk about as requirements, these are all storage account specific permissions. You do not need function app, RBAC, permissions, or whatever to affect or to perform these attacks, right? You just need storage account level permissions. So even though the storage account is technically a different service from the function app, you need to start thinking about storage accounts more of as like an extension of the function app itself rather than 2 separate things. So you need read access to containers, specifically that host.json blob, which is contained in that Azure Web Job Secrets container. And then you need write access to the file shares, and specifically, it's that source code or that defines the triggers, right? You need to be able to modify that. And then the ways that you would kind of get access to those is, in terms of RBAC, for example, we have the storage account contributor definitions here for this RBAC role. And really the thing that's interesting here is that list keys action permission. And it's not specifically listed there, but it's kind of contained under that wildcard under storage accounts. So be on the lookout for that because access to those keys will get you exactly what you need. And then also look out for custom rules too, because you never know what custom rules are going to have there. And then the other 2 direct access methods are, shared storage access keys and then SAS tokens. SAS tokens can be insidious because, the expiration dates, the permissions, and there's not a really good way to track those once they're kind of out in the wild. So be on the lookout for those. So that kind of brings us to how exactly are we going to kind of get this code on the function app so we can start executing our malicious code to either do decryption or return, decryption keys, right? So this is kind of came from Rogier, and I apologize if I'm mispronouncing your name, but please go read his blog. He has some great research on attacking storage accounts, and in his blog, he really covered the kind of overwriting of file share files, and specifically the source code for triggers. So he was kind of inserting himself or backdooring existing functions. So we're going to take that exact same concept, and what we're going to do is instead of overwriting something, we're going to create a new function. And we're going to do this by basically just creating a new directory. So under that SMB file share site www root, we create a new directory. Name it whatever you like, and then you're going to add your trigger code right under that. So if we are going to add a PS core trigger, we're going to add run.ps1 function.json and whatever else that you need to kind of make that trigger function. And obviously, this is going to vary by your programming language. And then what happens once you get everything uploaded there to that file share, you just wait. So the function app is going to kind of pull that storage account every once in a while, depending on a state change, and then it will kind of import that function depending on what it's seeing in its corresponding share files.
And in this case here, we see in the function.json, it's anonymous, so we basically can just keep pinging it anonymously until it shows up. If you have function level triggers, and we'll talk about that in a second, requiring a function key to call that, you wouldn't be able to actually call that. But if it's anonymous, you're basically putting code that you can execute out on the internet, out on an anonymous trigger, so be careful with that. But in our case, we basically just wait for the thing to populate, and then you can call it.
So we've got what we need, how we're going to do it, how we're going to kind of deliver this code to get us our decryption, but how does this actually work? So really, the core here of how this all works is ASP.NET Core Data Protection, and that provides the APIs for core cryptographic operations, key management, configuration, and all of that. And there's actually a specific Azure Web Data Protector that's being used by the function apps for this purpose. So if you take a look at that code there, and I didn't want to slap a whole bunch of code on a slide, but I did it anyway. So if you look at line 51 there, that's where you can kind of create your Azure Data Protector using that specific library, and then use that function-secrets kind of parameter there to create the specific Azure Data Protector for function apps. And then you can unprotect that right there below. So you can use this library directly within an ASP.NET Core function app trigger, which is pretty neat. And it's actually available on GitHub, so you can go and take a look at that. Right under the Azure organization, we have Azure Website Security, and that is all the source code for those helpers there. And this is important because this is used by Kudu, it's used by the actual function host itself, so it's a pretty important library when you kind of get down to it. And if you look at that social MSDN post right there, somebody actually tried to do this quite a while ago. And if you look at that URL there, it contains the word link, so that'll kind of give you a clue as to how old this post is, right? So the code there will fail, but we're going to take those core concepts and apply them to our use case here. So let's get down to it. Let's start decrypting those keys, right? So I'm not going to show you all of the source code here, but please check out the corresponding blog, and we'll post everything with the tool that'll actually have some of this code that you can go and take a look at. But basically what you want to do here is you're going to take that code, which again you're not seeing, but take the encrypted master key or whatever key you want from that host.json, throw that into the exploit code, and then we're going to use that exact same kind of overwrite or push to create a new function app within the storage account. And then at that point, the code should have access to everything it needs. The decryption keys within the environment variables. So all you need to do is, basically execute that trigger. So you either wait for it with a timer, use an HTTP trigger, and then that's how you get your decrypted keys or your unprotected master keys, function level keys, whatever you want. Return it to your web server or return it via web response. It doesn't really matter, and you can kind of see in the screenshots here, we're just using an HTTP trigger, firing that off to Burp Collaborator, and you can see that, I know it's really tiny, but these two values, trust me, they match. All right, so we can decrypt things within the container itself, but what if we wanted to do it offline? So the only thing that we really need here to do this decryption offline is that decryption key within one of those two environment variables. So we were kind of digging through the source code there of that repo we were just talking about, and in the constants.cs file, there's a lot of clues as to the names of environment variables and how that decryption is actually happening. So what you need access to is one of those two environment variables there, Azure Web Encryption Key or Machine Key Decryption Key. And depending on whether you're running on Windows or Linux, you're going to need either of those to kind of do it, but those two should work for you. So we modify our exploit code, and all we're going to do this time is just return that decryption key. That's all we need. Then what you're going to do is you're going to pull down that GitHub repo, set it up with your Visual Studio, get your development environment running locally, and you're going to take those two most important things, right? And you're in that test file there, data protection provider tests. You can just slap in and hard code some of that data there in your local environment, right? So the Azure website's local encryption key, you put that in as your decryption key up at the top, I think line 18. And then in line 26, that's where your encrypted material goes. You run this test, and it writes your unprotected keys out to a file. So pretty cool, because you can do all of that locally.
So to make this easier, instead of actually running everything in Visual Studio or Visual Studio Code, whatever you want, we actually just made a function app that does all of this decryption for you. We pushed the Funko Pop GitHub repo. We'll have links at the end here out to the NetSpy GitHub probably a week ago. So some of you might have seen that pop up on GitHub earlier. Tried to keep it kind of quiet, but there's a nice deploy to Azure button that deploys out an ARM template that deploys this function app into your environment. Now you can use this to decrypt these keys, assuming you get access to the encrypted key from the host.json, and get the encryption key out of the containers itself, and you just feed it into this web application. It's going to return it back to you here in the function app. So along with that, to help just make this process a little bit easier, we created a PowerShell function that helps you, I guess, automate the process of identifying storage accounts that have attached function apps. It'll crawl through each of the storage accounts that you have access to with your existing AZ PowerShell connected session. And for each one that has a function app, it will show you, we'll see that in the demo here, which function app is attached to it, and then you just select which ones you want to attack. It goes through, figures out which programming language is being used for each one, deploys the appropriate payload, and that will return the decryption key out of the container. Additionally, if there's any attached managed identities, we talked about those at the beginning, it will generate tokens for those for 3 different scopes, graph, management, and key vault, and give you those tokens back in the response. You can use those tokens for other stuff. We'll talk about that in a couple of slides here. And that gives you all that back in the PowerShell window here. You can then feed all of the keys and encrypted data into the Funko Pop app. Good to go. Let's see, so that kind of covers, okay, so it covers that. So we're gonna switch windows here because it's a little bit easier to control the video that way. Okay, so I'm gonna do this from up here. Hopefully we got the camera on here. So real quick, we are signed in as the SA contributor. We can see the 2 storage accounts we have access to. We can also see that we don't have any function app level access. And we'll show our IAM permissions here, show that we have storage account contributor with the user that we're logged into. So from here, we're going to hop over to PowerShell and show that we don't have a current context. We're going to connect AZ account with device authentication, use the device code back in the browser to log in as that browser authenticated user. Then we're going to run that invoke AZ function app takeover. I don't remember the name. I wrote it. I should know the name of it. But we're authenticating here. And now that we're authenticated, yep, function app takeover. I got it right. With the verbose flag, we're signed in as SA contributor. We're going to select our subscription. And it's going to start going through and identifying all of the storage accounts that have function apps tied to it. We're going to pause here in just a quick second. So it identified 6 different function apps in the, or 6 different storage account function app combos here. We're going to pick a specific one, the Linux PS one, which is a Linux-based PowerShell function app, and choose to exploit it. Now, I did fast forward the demo video here just a bit, because normally what will happen is once it's identified the language, it publishes the payload up to the file share, then waits 60 seconds for everything to actually get kind of spun up and recognized by the function app itself. Once we sleep for those 60 seconds, it will then just continually request the function until we get something back. And there we go. So we've got our encrypted master key, our encryption key for that, management vault and graph tokens, which then can all be used with REST APIs for those specific APIs. And we're going to go ahead and copy out our master key and the encrypted master key, or the encryption key and the encrypted master key out of here. And then pop that over to the function app that we wrote for this to automate the decryption for you. And then that should return the decrypted key value down at the bottom, and we'll compare those at the end to what's actually in the Azure portal, so you can determine that, yep, it actually properly decrypted. So 4NY32. And if we bring it back over, we can see that 4NY32 is the master key for the function app that we attacked. So this totally shows that if you have storage account contributor, or the ability to read and write files in a storage account that contains a function app, totally take it over, get the master key back, and then use that master key to continue to persist in the function app itself. There we go. So these are the languages that we currently support right now. Java doesn't get much love from us because we don't do a lot of Java stuff. So if anybody wants to do a pull request and help us out, that'd be cool. But everything except for Node, we're able to return the managed identity tokens. Node's a little fussy with making those managed identity calls. So that's what we currently support for functionality. And post-exploitation here, once we have those tokens, we can use those with the REST APIs to take actions in those different things. So if we get a key vault token, we can list out the available key vaults and potentially get access to keys and secrets, anything else that might be in that key vault. Additionally, with that function app key, take a look at the XM Cyber blog post that was mentioned at the very beginning. They have a whole rundown of what you can do with an actual master key or other keys within a function app. That gives you kind of the full rundown of what you might want to do with that master key. So we're going to change gears here a little bit, talk about another part of function apps here called the VFS APIs. We put a blog post out back in March about this, so some people may have seen this a little while ago, but we'll talk about it here. When you go to access files in the function app or within the functions under the function app, there's an API that's called the VFS API that's used to read the files itself. This used to be available to the reader role. This was a great place for us to find stuff during pen tests because people love to put credentials in here. There's credentials.json, and there's the service principal credential. Great, database connection strings, right there. We can read them as the reader role, which is often what we get during a cloud pen test because people don't want to give us contributor, because then we can make changes in the environment, and that's kind of dangerous. These APIs are still available for someone who has contributor, so you could technically replicate the same attack, but it's kind of a moot point there because you're already contributor and you can already access the things that you're going to try and access here. But that's besides the point. So there's two different spots, the app files and the individual code test here. Those both use that same API. And if we deconstruct that API, it's a management.azure.com API. Specifically, the host runtime admin VFS for the function app itself. The key thing here that we're going to care about is the relative path equals 1. If that's set to 1, that just gives you the application files that you normally see within the Azure portal. If we change that to 0, that gives us the root file system on the container, be it Windows or Linux. So for the Windows option, we don't see a whole lot. It's actually pretty quiet in the Windows containers. The worst of it is getting access to the data protection keys for the ASP.NET containers. That's about the most sensitive thing you can get access to, and even from then you still need encrypted data that's encrypted with that to actually decrypt anything, so it's not hugely impactful. This was actually the first thing that we reported from these APIs to MSRC, and they eventually just wrote it off as info disclosure low because, yeah, I get it, that's fair. It's a pretty low impact if you're getting those keys. However, if we go to the Linux containers and use that relative path of 0 and get to the root file system, we can actually access the proc folder. And for those that are not familiar with proc, that's where all of the process information lives. So proc/self, you can get your own current process IDs, environmental variables, the command line invocation that was used to run the command itself, all sorts of good stuff. We have a NetSpy blog from quite a long time ago that gives you a full rundown about that. Go ahead and look that up. That's really helpful. But what we did is identified that we could kind of directory traverse to the environmental variables for each of the process IDs and went through each of them and noticed that there was the container start context SAS URI. And this is a storage account URL that points out to a storage account controlled by Microsoft. It's SAS tokened, which allows us to read the startup context configuration for the container itself. Also in that environmental variable section is the container encryption key used to decrypt that startup context file. If we go to the next one here.
Yeah, like 2 minutes.
Okay. We can see the encrypted context right up here that has the initialization vector. We use that with the key that we pulled from the environmental variables. We can decrypt all of that startup context. That includes the master key, the function key, any source code files that you might want, as well as any app registration credentials. They're tied to integrated Azure Active Directory auth. So really sensitive stuff. And it allows us as a reader, or previously allowed us before they fixed it at Microsoft, to go from a reader on the function app to get access to the master key for the function app, take over the entire function app at that point. So we can jump ahead here. So Microsoft remediated it. They didn't remove the API, but restricted the permissions just to contributor. So technically, you can still replicate this. We have some PowerShell code right here that you could technically use to replicate the same thing at this point if you really wanted to follow along and do it. But yeah, if you have container command execution, let's say you get command exec through one of the function apps, you could technically replicate this as well and then get access to the master key.
So some quick best practice guidance here, and we're going to upload this, but in terms of just best practices here, just least privilege. Wherever you can apply it, do it, right? Because these two vulnerabilities that we've seen here, they work in kind of weird ways. And sorry, one of them is a vulnerability, the other one is expected behavior. But they behave in weird ways, right? So whenever you can limit scopes, limit permissions, wherever, make sure to do that, right? Protect your storage accounts. Don't, lose your shared access keys or SAS tokens and store them in clear text, because somebody will find them. Limit permissions on function app identities, and especially if you have something that's very highly privileged, permissions that's granted to a function app, make sure you protect that, and that's almost keys to your kingdom there, depending on how privileged it is. For your function apps and storage accounts, make sure to use dedicated resource groups. You don't want to be, mixing some of your application function app, assets in other things, because if you're starting to grant access at the resource group or the subscription scope, that's where you're going to start to get into trouble. And then for logging, make sure you've got those diagnostic logs enabled. Look at your control plane logs, look at your data plane logs for, activity like this. And then Microsoft's official recommendations, you can use key vaults to kind of store your keys, so they're no longer within the storage account themselves, which kind of starts to take away that vulnerability there if you're kind of storing them in key vaults. But if you still have write access to the file shares and you can get access to the managed identity, then you kind of have the exact same issue, right? You can also use VNet integration to kind of hide those storage accounts away, so you may not have direct access to them. And take a look at all of these links here. There's a lot of good recommendations from Microsoft in terms of how you can actually just protect your storage accounts from attacks like these, right? And in terms of disclosure timelines, you can kind of see them there. We try to make sure we go through responsible disclosure whenever we talk about stuff like this. So this is just the timelines and the reports that we've created. All right, and special thanks to everybody on that previous research slide. Seriously, that's great work there. Please go and read those. And we wouldn't be here talking about some of this weird stuff without the previous research of everybody up on that slide. So yeah. Thank you to everybody for coming out, and I'm not sure how we are on time, but we will certainly be hanging around afterwards for some questions. But yeah, any thoughts?
Yep. We got two. Okay, we could probably take a couple of quick questions here. Yep.
So you mentioned that Kudo is kind of the underlying attack vector that you're leveraging to run this script, right, underneath, if you get PowerShell. Now, when I look for disabling Kudo under the MCSC, it's very, very difficult to actually find and how to do that.
Yep.
Is that something you might want to add to your slides that could eliminate that vector?
So the question was disabling Kudo for the SCM interface within app services. It's really hard to do. We've worked with clients to help them disable it in the past. That's definitely a recommendation we probably should have included, along with protect your function apps so they don't get command execution in the first place. But yes, very good point.
You can firewall them off.
You can also firewall that off on the Kudo interface.
Right, agreed.
Yeah.
It's just, if you have a public SaaS, or a public PaaS, I should say, it's still there.
Yes.
Making sure that you are, when you talk about your subdomain, making sure that it's non-existent so you can block it, so somebody can't side channel it.
Very good point. Question?
So from the blue team perspective on the first scenario, if you're basically trying to enumerate all the storage keys and everything after you're on the master key and everything else, you're still going to be associated with your identity with the contributor role when you're trying to run those commands and everything else, right?
So the question was from the blue team side, detecting, scanning all of those storage accounts for potential permissions and getting keys to go right to the function app directories, correct?
Effectively, like once you go through the entire process and everything as a post-exploitation activity and everything else, and you're trying to enumerate all the storage keys in the account and such.
Yes.
That's going to be tied to your contributor account that you're using, right?
Correct. So the question was if this would be tied to the account that we're running the PowerShell script to do the actual execution on this. Yes, that would be tied to that specific account. However, where it gets a little weird is the function apps really don't have any detections built in of like, hey, somebody added a new function to the storage account and we're now running it. That's kind of a weird bypass.
So the quirk on that one is the sign-in logs and everything else for the things might be containing those records and everything when you're trying to enumerate the storage key, so it's no longer associated with the function app and everything because it's at the storage account level. So
Correct. Yeah, everything's tied to the storage account level, and from a enumeration perspective, we really just, I guess we do list keys to actually get the files in there. So yeah, that's a good point.
There's
Yeah.
a behavioral pattern that if the user's kind of seeing what you expect to see from them, then success on it. So
100%. And for context, Microsoft does seem to keep tabs on the microburst repo that we have, and seems to add new detections every time we push a new script. So I wouldn't be surprised if this gets caught with Defender for Cloud pretty soon. So your mileage may vary. I think we'll probably have to wrap up here, but thank you very much, everybody. We'll hang around. We can answer some more questions out here. So thank you.